guys, so today we're going to talk about the different states of matter and how intermolecular forces are related to the states of matter. So first off, intermolecular forces are forces of attraction between particles, which is why they can also be called interparticle forces. They can occur between atoms or they can occur between molecules. So interparticle force really does describe them well. Okay, so they depend on the distance between those particles and the charge. Right, so all forces of attraction, Coulombic attraction, depend on those two variables, distance and charge. Now in this case, charge could actually not be a true charge. It could be the polarity of a molecule and the strength of that polarity, okay? It's important to understand that these forces of attraction are not chemical bonds. The chemical bond happens within the molecule itself. So if I have water, my chemical bond would be between the hydrogens and the oxygen. The attraction for one water molecule to another is going to be an intermolecular force, okay? So intermolecular forces are not chemical bonds. Those would be, covalent or ionic. Okay, so when we're discussing intermolecular forces and their relationship to charge, the increase, so along here, the side here, an increase in charge is going to cause an increase in attractive forces, right? An increase in attraction. And so the greatest interparticle force is going to be ionic, because in ionic bonding you have true charges, right? You have positive ions and negative ions. And so the ionic attraction increases as the charge of those ions increases. So if it has a positive 2 or a positive 3 charge, it's going to have a greater attraction than a particle with a positive 1 charge. And it also increases as the size of ions decreases. So the smaller those ions are, the greater the force of attraction between them. And that's because the nuclei are actually closer. Okay, so the next greatest force of attraction is going to be a dipole-dipole attraction, and that's the attraction between the dipoles. And so dipoles are just like the positive and negative, right? Di means 2, so a dipole is a molecule that has both a positive and a negative, right? So if I have the positive of one attracted to the negative of another, then that's going to be dipole-dipole attraction. Now that happens with polar molecules because they have those permanent dipoles, right? They have the permanent negative and positive ends. Now this is greater for more polar molecules, right? So the greater the polarity of the molecule, the greater this force of attraction. And the greatest force of attraction between two polar molecules is going to be hydrogen bonding. Again, because hydrogen, since it does not have electrons surrounding it, tends to be extremely, positive. When we're talking about dipoles, it's going to be sort of the positive end of that molecule. And so those polar molecules that have hydrogen have really strong dipoles, and so they're going to have a really great force of attraction. The next force of attraction is ion-induced dipoles. So that happens between ions and nonpolar molecules. What ends up happening is the charge on the ion actually causes the nonpolar molecule to have a negative and a positive end, to have a temporary dipole, and it's a pretty strong force of attraction. Dipole-induced dipole is between polar molecules and nonpolar molecules, so it's kind of the same thing. Those polar molecules cause temporary dipoles to form with the nonpolar molecules, and there's a force of attraction between them. And then the weakest force of attraction is going to be just induced dipole. Those are otherwise known as London dispersion forces. And again, that's an attraction between nonpolar molecules. What happens is you get kind of an electron shift. The molecule becomes temporarily polarized. It gets a temporary positive and negative end. Now this increases as the size of the molecule increases. So the greater number of electrons is going to cause greater electron shift, right? Which means greater temporary polarity. So you end up with sort of a more charged positive and negative side of that molecule, okay? Okay, so then let's talk about intermolecular forces in relationship to distance, right? And so we know the states of matter, correct? We know solid, liquid, gas. A decreased distance between particles, so the closer they are, is going to increase that attraction. So in gas samples, those particles are really, really spread out far apart from each other. And so since they have the greatest distance between particles, they're going to have the least attraction. In fact, we say that intermolecular forces tend not to exist in gases because they're just too far apart from each other. With liquids, those particles are not arranged in any way, shape, or form. They're moving past each other. In liquids, they can constantly move. So there's no real structure here to this. They are pretty close to each other, right? So there's going to be high attraction. And again, there's little distance between those particles, but they are far enough apart from each other that they can move past each other. In a solid, they are mostly arranged, most solids, not all, but most solids have a structured arrangement of particles, and they're pretty much as close together as they could be. And so since there's the least distance between particles, they are actually going to experience the greatest attraction, the greatest intermolecular force. So talking about solids, there are several types of solids, and we're just going to go ahead and discuss those now. Solids can pretty much be grouped up into two large groups, okay? So you have the crystalline solids versus amorphous solids, okay? So crystalline solids are the ones that have a very, very organized structure. All of the particles are held in what we call lattice points. So think about that like a grid, okay? Think about those particles being held in a grid, in a specific place within that grid. And so there's four types of crystalline solids. We have four types of organized solids. The first one is ionic, okay? So that's where you have positive and negative ions that are being held in those lattice points within that grid. And they're held together by Coulombic attraction. Right? There's that attraction between the positive and the negative ions. And again, we talked about how those charged particles, when we change the charge or we change the size of the particles, that increases the attraction, right? The next type of crystalline solid is a metal, right? Metallic solids. And so that's going to be metal cations. Again, they're going to be positive because they've lost their electrons. They're surrounded by those electrons. And while those electrons may not be held in specific lattice points, the cations actually are, okay? And again, they're being held there by their attraction to that sea of mobile electrons. And so, again, they're held together by Coulombic attraction. The next type of solid is really different. It's an atomic network solid. So these are sometimes called network covalent, because what ends up happening is you have atoms of nonmetals held in these lattice points. Now, they are held together there not by Coulombic attraction, but rather by covalent bonds. So these atoms tend to fill up their valence shell by covalently bonding to the other atoms that are around them. So you'll notice that this happens a lot with nonmetals like carbon, silicon, phosphorus. A lot of these can form covalent bonds between atoms, and so you end up with like one giant molecule. Diamond is like one giant molecule where carbon has literally bonded to the atoms above it, below it, and side to side. And so since it's filled its valence shell by bonding to all the other carbons around it, it becomes a very, very strong substance. And then we have the last type of crystalline structure, that's going to be molecular solid. So that's when we have covalent molecules that are held together in lattice points. So I might have carbon dioxides in the points in that grid, right? Now, they're not covalently bonded to each other, the carbon dioxides. The carbon is bonded to the oxygen to make the molecule carbon dioxide, but the individual carbon dioxide molecules are attracted to each other by intermolecular forces. So it's those intermolecular forces that hold together the molecules in a molecular solid. Okay, and then the other group of solids that we don't talk about as much is amorphous. And so amorphous just means that there's really an unorganized structure. There we go. Okay. It's made up mostly of silicates. So silicon and oxygen compounds, right? Mostly those are going to be the ones that make up these amorphous solids. And so a lot of the ones that you guys are familiar with, glass is an amorphous solid. Ceramic is an amorphous solid, and clay. And so you end up firing these, heating them up, these different silicate compounds, and they do kind of form intermolecular bonds between them, but not in any kind of structured way. So everything's just kind of positioned all over the place. It's not in a specific position like it would be in a crystalline solid. But that does give some give to the substances, and so you end up having things that you can shape and then become very brittle later, right? But these are definitely useful solids. So anyway, that's just kind of an overview of the different types of solids and the intermolecular forces that hold them together. And thanks for listening.